So our ability to synthesize DNA, our ability to do robotics, our ability to do cell selection and cell sorting will expand our ability to generate experimental data that will feed into these AI tools. So I honestly think that this is going to be really sort of a positive spiral where as they get more data to advance their tool, then they will have the opportunity to do more collaborations and more molecules and so on and so forth, and that will advance their tool. I think that we will rapidly discover that there aren't going to be significant limitations on the experimental side.
Welcome back to the Smart Biotech Scientist podcast. Today, we are continuing our conversation with Susan Sharfstein, who is a professor of nanoscale science and engineering at the University of Albany, New York. We will be exploring how AI is revolutionizing protein structure prediction and manufacturability assessment. Let's dive in. Are you juggling the complexities of CMC development while trying to enjoy the beauty of biotech? Have you ever wondered if there's a way to simplify bioprocessing? Welcome to the Smart Biotech Scientist podcast, where we're diving headfirst into the very challenges you face. We're breaking it down, demystifying the jargon, and giving you the keys to unlock your full potential. I'm your host, David Brohlman, and I get it. With 15 plus years in the biotech industry, I face the same challenges you do. There's a way to simplify and streamline so you can remove complexity, you can skip trials and errors, deliver without delay your groundbreaking therapy to clinics at market, and still enjoy every single step. Do you want to learn how industry experts and I did it? Grab a cup of coffee and your favorite notebook and pen. Now is the time to take your bioprocessing game to the next level. Let's smarten up biotech.
Definitely, we have now a lot of technologies at our disposal, AI and silico models and so on. Before we dive into that, I would like to touch upon another point, because are there some simple or some obvious pitfalls we can avoid or things you have seen in your research work and your collaboration with UCB Celltech?
I don't know if I would say pitfalls, but that I mentioned, right, this alanine glycine. So one of the things that actually turned out that they saw this alanine glycine in multiple molecules. And the other thing that was really interesting is that both the alanine and the glycine variants occur in nature. And it turns out that the glycine variant actually is more common than the alanine variant, even though the alanine variant is the one that expresses much, much better. And so I think perhaps one of the take-homes from that is to remember that what we do in the biomanufacturing space is not really what nature intended. That, nature never intended for cells to be making grams per liter, to have, necessarily specific productivities of 100 picogram per cell per day in a bioreactor. We should take lessons from nature, but we should take them with a grain of salt, understanding how the biomanufacturing world is different. And the other thing is sort of the flip side of it, that we did hybridomas and lots of people did hybridomas. And because people had this mindset, well, okay, B cells make antibodies, so therefore we should make antibodies in B cells. And if we were stuck in that mindset, we would still be back where we were in 1980. And nobody would have ever thought that the ovarian cells of Chinese hamsters would be the workhorse of the biotechnology industry. Not to let that biology is important. I mean, it's sort of the fundamentals. But on the other hand, don't let what nature does define what we do in industry, because there are ways that we can exploit nature that nature probably hadn't thought about.
I like how you put it. Yes, definitely. I think we have seen a lot of breakthroughs, a lot of surprises in our industry. Yes, nobody would have thought that we would be using CHO cells. And now this is a good transition to AI because AI obviously is here. AI has brought already a lot of surprises, and I think we will be up for a lot of surprises in the future. Now, you have a collaboration with DeepSeq AI, and which is particularly interesting. So could you walk us through a bit how you are using AI tools to predict protein structures and also potential manufacturing bottlenecks or challenges?
A little bit. Okay, so I have to say that I am not doing any AI. All the AI is being done by the company, but what they are interested in is really creating a data set to understand expression. And so they've done some work previously with peptides where they have been able to use their AI tool to predict which peptides have high levels of expression. And what they want to use their AI tool now is on VHH single domain camelid antibodies. So what the plan is, they're going to send me a library of 10 to the 6th sequences, and we're going to take these and we're going to put this library into CHO cells, and we're going to see which sequences express well and which sequences don't. And then they're going to take that back to advance their AI tool. The subtleties of their AI tool are beyond me, other than to say that they pointed out in their grant that, it's not AlphaFold or anything like that, which of course recently got the Nobel Prize for developing AI to understand protein folding. So I think that their idea is to approach expressibility in a different way. But again, I am not really privy to their AI tool. And I think even if I were, I wouldn't really understand it. But I'm really excited about it because this is one of the things that I've been really, really wanting to do. And so I've talked to people who, have background in protein chemistry and things like that about pulling sequences from databases and trying that. But this is really a much better approach because it really allows us to really, really explore phase space in a much more comprehensive way that should give us a lot of data and a lot of insight into what leads to good expression. They're also interested in doing temperature stability as well. The molecules that we make in CHO cells, they're also going to do phage display and look at temperature stability. And because I think that's a lot of the goal of their AI tool is to look at multiple aspects of protein engineering. So I think that this should give us a lot of insight, of course, on VHH, but also ultimately what I think they hope is that they will then be able to take that and use this information to then extend to more complicated molecules.
Yes. So the question I have now is, well, obviously it's still very early and we don't know what future AI holds for this prediction. We do have certain in silico models already that have been around for a while already. So what is your prediction or gut feeling of how predictive that will be or how much better AI will be versus to what we have? Or where do you see limitations in the prediction of the manufacturability?
That's a good question. I think, so part of what they're doing, of course, is they're using generative AI to develop the sequences and things like that, which I think has significant potential. And I anticipate that generative AI will allow them to have significantly more predictability. But the limitation ultimately on any AI tool, right, is that AI is only as good as the data that you give it. And so I think that that's going to be the real crux of it is that, which of course is why that they are collaborating with me, right? They submitted a proposal once and they got some feedback. Yeah, it was really, really interesting, but they don't really have any mammalian cell culture expression experience. So I think that that's really the key, and I think that's the key, honestly, between almost any, in silico tool and any developing a useful in silico or AI tool is that ultimately you've got to have experimentalists to test things because there's just not enough core knowledge about expression, right? That just because a protein folds doesn't mean that it will express well. Now, if a protein folds badly, it's likely to express badly. But the converse isn't necessarily true, that you can have a protein that you can fold really well in a test tube, but can be very, very difficult to make in a CHO cell.
Yeah, that's where I see the limitations with AI because I'm really curious about how we can solve that. Because, yes, we need to test that in a wet lab because if we don't have accurate data or high quality data set, the model will not predict what we want it to predict. But now, since you have to express all these molecules in a lab, you will be limited by the number of molecules you can express. A question I have, how can we still leverage the power of AI with such small data sets?
Yeah, well, so our target is 10 to the sixth. But I honestly think, the other thing that's happened in the industry is robotics, right? Actually, I do have some robotics in my lab, but I think with serious robotics and also with a lot of the technology that we have now for cell sorting and cell screening and things like that, probably, if they can demonstrate the efficacy of their tool, that they will probably have no difficulty finding some big biopharmas to collaborate with who then really are in the position to do 10 to the 8th, 10 to the 10th molecules, right? So I think that ultimately will not become a barrier. And, the other thing that has happened is that making DNA is now dirt cheap, right? It used to be that to make a big piece of DNA, that was a lot of hassle. And they are actually doing some PCR on this because of their goals, but there's no reason that amount of DNA, that length of DNA, you can synthesize entirely. So our ability to synthesize DNA, our ability to do robotics, our ability to do cell selection, cell sorting will expand our ability to generate experimental data that will feed into these AI tools. So I honestly think that this is going to be really sort of a positive spiral where as they get more data to advance their tool, then they will have the opportunity to do more collaborations and more molecules and so on and so forth. And that will advance their tool. I think that we will rapidly discover that there aren't going to be significant limitations on the experimental side.
Oh, wow, that's great to hear. I love that approach because, yes, if you rely on various labs and various partners, you can multiply it by several orders of magnitude, and then you will have the number of experiments you need to get a meaningful model.
Right. And particularly when your partners are people like Genentech and things like that, as opposed to academics.
Yeah, absolutely. I would love to hear from you guys again in probably in 6 months or in a year or so. Let's see where this is going. We definitely should set up another podcast episode. Before we wrap up, Susan, I would love to ask you this question because you have such an impressive career journey and we have some younger people tuning in. So I'd love to hear what advice would you give your 25-year-old self just starting out in chemical engineering and bioprocessing?
I think my 25-year-old self was more arrogant and dismissive of things that I didn't necessarily understand. So my 25-year-old self really thought that sequencing the human genome was a lot of waste of money. And boy, was I really, really wrong about that. I think that I would give my 25-year-old self the advice that be really, really open to everything because you have a lot to learn. And what you know now is only really a small piece of what you're going to know as you go out through your career. The other thing that I've come to realize in my 25 times 2 plus some, that the people, the mentors that you choose or wind up with are probably the most important thing, will have more impact on your career than you might realize.
Oh, I love that. Thank you so much for this priceless advice, the $1 million advice. Get mentors. Be open-minded. Thank you very much, Susan. From all what we have discussed today, what is the most important takeaway?
So I think it actually comes back to the first question, right? Which is part of the reason I really, really like working in the biomanufacturing field, and I love training young scientists, is because I really believe that the biopharmaceutical industry has the potential to offer life-changing and life-saving medications and treatments. I have a friend who has glioblastoma, and I am not super, super optimistic, but I keep emailing his wife saying, CAR T cell therapies. They're doing clinical trials in CAR T cell therapies for glioblastoma. And I think that that is the only thing that I see on the horizon now that has a potential for a cure. And there's so many things that we could not cure 30 years ago that we can because of biomanufacturing. And that's a great place to be.
Yes. Thank you for all your amazing insights, for sharing your expertise, Susan. Where can people connect with you?
Well, because I'm an academic, you can Google me. I'm Susan Sharfstein at the University of Albany. I'm also on LinkedIn, and I even have a website now. I actually do read and answer all my emails, and I'm always interested in collaboration. So I love collaborating with companies. I really enjoy placing my students in companies. I love working with small businesses because it's fun and I get exposed to novel things. Absolutely reach out to me either by email or on LinkedIn, and I actually even respond to most of them.
Smart biotech scientists, you've heard it well. The door is open. Contact Susan, explore collaborations, use that opportunity. I will leave all the links in the show notes. And thank you so much, Susan, again for being on the podcast. It's been a huge pleasure. And I look forward to part 2 somewhere in 6 months or in a year to see the progress of your study.
Great. It was a pleasure being here and very lovely talking with you.
Thank you for joining us for this deep dive into AI and protein manufacturability with Susan Sharfstein. Do you want to transform your bioprocess development? I help CTOs cut through complexity and accelerate time to market. If this is for you, book your free strategy call at brumanconsulting.com. And thank you once again for tuning in, and I'll catch you next time. All right, smart scientists. That's all for today on the Smart Biotech Scientist podcast. Thank you for tuning in and joining us on your journey to bioprocess mastery. If you enjoyed this episode, please leave a review on Apple Podcasts or your favorite podcast platform. By doing so, we can empower more scientists like you. For additional bioprocessing tips, visit us at smartbiotechscientist.com. Stay tuned for more inspiring biotech insights in our next episode. Until then, let's continue to smarten up biotech.